Welcome to the 4.8 notes. We're going to be looking at something called the Lagrange error bound. And so we've talked a little bit about error, but we're going to have a different way to think about it with errors made with Taylor polynomials specifically. So just some background vocabulary to make sure we're all talking about the same thing. And this is taken from Paul Forster in Alamo Heights. And so these are his information below. So let's say that f of x is some power series. Now you might remember when we talk about a power series, we're talking about a series that has both x and n in it as variables. The partial sum would be the sum of a certain number of the terms, maybe like the first three terms or the first four terms, etc. The tail is the rest of the series because we're looking at infinite series. So the tail is everything else, all of those other little terms. The remainder is what you get by adding up all of those terms in the tail. Now, what we could say is that the true value of f would be the partial sum that we've got so far, plus the remainder, the sum of all of the terms in the tail. The error is the mistake, or is the little bit that you're off by assuming that f of x is the partial sum. And so by your approximation. So when we talk about the partial sum, that's like our approximation. And the error is how far off we are, that approximation, from the true value of the infinite series. Now, the error is the same as the remainder because that's how far off we will be. It is a challenge sometimes to calculate exactly what that remainder is. Most of the time, what we do is we have like a bound for the error. So we usually have something where we have the error is going to be something that's bigger than the absolute value of the remainder. Now, we've done a little bit with this with alternating series, and we said the error was known to be greater than the absolute value of the next term because what we found, since in an alternating series that converges, that's what we mean by meeting the three convergence hypotheses, okay, those three conditions. Since the terms are alternating, decreasing in magnitude, and the limit of the terms of the individual expression for the terms approaches zero, what ends up happening is the next term, its magnitude, is going to be bigger than the sum. And that's because of the alternating and decreasing nature of the remaining terms. And so this is how we handle it with an alternating series. Now, what the French mathematician Lagrange found out is he developed a theorem about the remainder or the error. Okay, so when we talk about error and we talk about remainder, those are the same things. Okay, that's also called the error. And what he said is it is equal to the first term of the tail if the derivative is evaluated at a really specific place. Now, normally we evaluate the derivative of each of the terms around the center. But if that derivative for the very next term is evaluated at a place that's different than the center, but at some value z, okay, so z is going to be in between our center c and the value of x that we are evaluating the function at. That wherever z is, now what the heck is z? Z is going to be a place that would allow us to find a maximum for the derivative. Now, what ends up happening is calculating exactly where z is not something that we're going to have enough information to do in the type of problems we're looking at, but we're going to have a way of knowing what that max derivative would be. So they're going to tell us some information somewhere in the problem in a variety of different ways to know what that max derivative is. So this would help us see the Lagrange error bound. So in regards to Taylor's theorem, and this is really what Lagrange's error bound is talking about. Remember, error bound is helping us find the maximum error. Okay, the maximum error here is really what we mean when we say an error bound. Bounding the error, the most the error could be. So if we've got a function f and it's differentiable through all terms, including like the nth plus 1 term, and there's an interval that has the center c. Okay, so the center might be at 0, it might be somewhere else, but c, that interval needs to have c inside of it. Then for every x value in the interval, there is going to be some place z, and z, remember, is going to be in between the center and wherever we're going to evaluate x, such that when we look at the remainder, okay, so like this is our partial sum, and then this would be the remainder, which will also tell us what the error is going to be, or the max of the error. We can find out what that remainder would look like if we take the derivative at this very special place, z, and then we go ahead and we use our regular rule for Taylor polynomials, where we have x minus c raised to whatever power the derivative is at, and then divided by that, the factorial of that same amount. Okay, so this is still our formula for Taylor polynomial. But what this is this is the next term. If our general term is in terms of n, the remainder here could be modeled by this. Now, again, what we're doing is we are saying we're not just finding our derivative at the center, we're finding it at some other point z. And what ends up happening is specifically we're going to look for where are we going to be able to have this maximum for the derivative. Now you might notice that we have all these absolute value bars in this next part. That's because you might remember the error or remainder, those are both talking about the same thing, we want to be positive. Okay, so this is the error or the remainder. Those are both great ways of saying the same thing. We want that to be a positive. So we want to make sure that we're looking at positive values on here. And we want to find this place where our derivative is the maximum. And so we're going to have a way to do that. They're going to give us some information to allow us to do that. Now, quite often, we'll be looking at specifically places where n starts at 0. All right, and so Taylor's theorem is going to tell us that f is going to be differentiable in some interval where c, the center's inside of it. And then this right here, this is just kind of an interesting connection that's kind of interesting to help us understand that this is the spot. If we look at like that first term where n is 0, this ends up being our tangent line approximation, which is a kind of interesting thing, which if we take this tangent line approximation and we subtract the f of c from both sides, this is like our y, which is another way to say f of x, is each equal to our derivative or our slope times x minus h plus k. Well, here's a different way to write that. F of x is equal to f of c, wherever the center is, plus our derivative, evaluated at some special spot z, is equal to x minus that center, c. Well, that's like our hk. Well, let's say that you then move the f of c over to the other side. And then let's say you divide by that quantity x minus c on both sides to get f prime of z alone. This is the MVT. It's slightly different in its notation, but you might remember the MVT says for a function that is differentiable and thus continuous, that f prime of c would equal f of b minus f of a over b minus a at least once. Now, that's not anything you're going to be testing on. It's just an interesting thing that all of this is connected. All of these things are connected, which is kind of weird. Like here we are working with like Taylor polynomials and Taylor power theorems, and there's a connection to the MVT. So what will you be asked to actually do? Well, you're going to be using Taylor's theorem to find the Lagrange error bound, which would be the maximum error. You are not actually going to be able to find out exactly what z is. If you could do that, then we wouldn't need an error bound, which is how we kind of approximate the most the error could be. We could actually find the exact error. We're trying to find the most it could be. That's what we mean by error bound. We're trying to find the maximum error. That's what we're working on by looking at the remainder. All right. So that the error, I wonder if I wrote my inequalities backwards up here. I sure did. Yeah. Sorry. Okay. So wrote that backwards. Super, super sorry. All right. So now, just so that you guys kind of get a sense of different ways that they might ask for that, they might ask for the error bound. They might ask for the remainder. Or they might ask something like this. This was an old AP FRQ way back from 2011. And there was something like this on there. And students had to recognize that this was another way of talking about error. This was another way of talking about error, that our approximation from a partial sum of a Taylor polynomial, this would be like the first four terms, compared to the actual value of the full value of f, if we including the remainder, that we were talking about the error being less than some certain amount. Now, this part down below here is not going to make sense to you yet. That's okay. We're going to make more sense of this as we practice it a bit. Okay, so for this first example, let's say we're talking about some function f, and we know some derivatives. And these are all evaluated, you're noticing, at 2. That kind of tells us our center for this is 2. So that's something that we should kind of notice, that the center is 2 because we're evaluating all of these derivatives at 2. And so we have the value of f of 2, f prime of 2, f double prime of 2, and so forth. Then we have a graph of the fourth derivative at x. And I'd like you to notice that it's on the interval from 2 to 3 and that the center is part of that interval. Okay, so what we want to do is first we want to find the third degree Taylor polynomial. Remember, third degree means we want x to be raised to the third power. So the third degree Taylor polynomial, I'll call it p sub 3 of x since it's the third degree, would be f of 2 plus f prime of 2 times, now that's the first derivative, so this would be x minus 2 to the power of 1 over 1 factorial, which I won't write that. If you'd rather, you could write this as a minus. Your choice. And then the second derivative would be a negative 1/5, and this would be times x minus 2 to the second power, and this is divided by 2 factorial, or 2. And when we need the third one, so we need the third derivative, which is 3/7 times x minus 2 to the third power, sorry, over 3 factorial. This is my third degree Taylor polynomial. We could simplify it if we wanted to. Totally up to you. So lots of different ways, like you could write this denominator as a 10, or this one as a 42, because that'd be 7 times 6. Now we want to use that answer to approximate f of 2.8. So what you should do right now is use your calculator, and you would take this third degree Taylor polynomial that we just wrote, and you're just going to replace x for each of these terms with 2.8. So why don't you pause the video and do that really quickly and see what you get. When you're ready, you can restart the video. I'm not going to show the typing of all of that because I know you know how to type, but this is 3.706 for the approximation. Now this is a partial sum. This is a partial sum because we only use the first 4 terms to get the 3 degree Taylor polynomial. There were other terms. This is an infinite series here. So there's a remainder or a tail. There's some error here. So now I want to use some information from the graph of the fourth derivative, which I have information about the fourth derivative on a very limited little window here, to show that the absolute value of f of 2.8 minus p of 2.8 is less than 1/8. Is less than 1/8. Okay, so what is this talking about? This is talking about my error, or the remainder. And I'm going to use the Lagrange error bound here to do this. Okay, so my error here could be found by looking at the remainder, and what Lagrange said for this is that we can find that remainder. What I'm using right now is this. Okay, so you have 2 pages in front of you, so you can kind of look at that as we're doing this. So what I'm going to be doing is I'm going to see my error would be coming from the absolute value of the remainder after the third term. Now the remainder after the third term is going to be looking at the next term. which means I want to be looking at the maximum of the fourth derivative evaluated at some x value of z. And now I want the absolute value of that because we could have a different sign. Now, if my formula for Taylor polynomial would use the fourth derivative here to find this next term times x minus my center, which we said was 2, raised to that same power as the derivative, divided by 4 factorial. This is what the remainder would look like. This is what the remainder of this would look like. So this error, which would be coming from that remainder, should be less than or equal to the maximum here of that fourth derivative on the interval that I'm giving. Actually, I'm going to write the word max when I evaluate. Well, what would be the maximum of that fourth derivative? I guess I can write it here. I'm changing my mind. It doesn't matter too much. I just want somewhere to communicate that I know that that's the maximum. So here's the graph of my fourth derivative, at least on a limited scale. This needs to include the center C, which is at 2, somewhere as one of the x values on my little interval. Well, what's the most that the derivative is? The derivative here is the height of this. So the most that the derivative is 7. That's the maximum fourth derivative times, now this would be x minus 2, but I'd like you to notice that what are we using for x? We are using 2.8 for x. This was x minus 2 to the fourth power. I'm going to use 2.8 minus 2 to the fourth power over the fourth factorial. And then I'm going to use a calculator from here. And this is from here where I'm going to go ahead and evaluate my error. I don't like the way I did this. I don't like the way I did this. I'm going to go ahead and write this in terms of x first because I have this right here as an x. Please forgive me. I'm not feeling super great today. All right. Now I'm going to go ahead and I'm going to now find the remainder specifically at 2.8. Which is what this is. This is my error or my remainder when x is 2.8. So now I'm going to take this expression and I'm going to say that this would be less than or equal to. Now, if you wanted to connect this, you could say that is the same as the f of 2.8 minus p of 2.8. And this should be, according to what we have from the Lagrange error bound, this should be less than or equal to what I have here as my formula for my remainder, but I'll evaluate it at 2.8. I did that a little earlier, but I would have had a linkage error because this says x, and I need it at 2.8. So this will be 7, absolute value of 7 times 2.8 minus 2 to the fourth power over 4 factorial. Now, we're going to go ahead and we're going to use a calculator for both of these. This is calculator active here. And so this would be 0.119 as my error, which indeed is less than 1/8. Now, sometimes people get a little stressed. I've got these equals and I've got these less than or equal to, but between any two of them, these are true statements. The remainder is going to be representative of the error. And according to the Lagrange error bound, that error will be less than or equal to the maximum of the next derivative, in this case, the fourth derivative of my new value of x, 2.8 minus the center, raised to the fourth power over 4 factorial. And that's 0.019, which is less than 1/8, because 1/8 is, I think, 1.2 or 0.125. 0.125. So this is our first example of using the error bound. It kind of reminds me of an alternating series where you're using the absolute value of the next term. Because since we approximated this at degree 3, we had to go to the fourth degree term. The difference is our derivative is not chosen at the center. If we look at this graph, the center here is 2, but we didn't use the fourth derivative evaluated at 2. We used the maximum fourth derivative for some interval that x is inside of. Now that 2.8 has to be on this interval somewhere. And the center needs to be on the interval as well in order for us to do this. All right, so let's take a look at the next one. If you feel like you're kind of holding on to this, okay, maybe pause the video and try this on your own. Now, the first part is basically like questions 1 and 2 in the last one. So you should be able to do this. Make sure you look at where the center is. And when you're ready, restart the video. All right, so for this one, again, we're writing a third degree Taylor polynomial. And so I would have 6 plus 4 times x minus 2 to the first power over 1 factorial minus 7 times x minus 2 to the second power. Think about that, over 2 factorial, and then plus 8 times x minus 2 to the third power over 3 factorial. Now, I'm not doing plus dot 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 because it specifically tells me third degree, so I'm stopping. That's what they told me to do. I'm going to use that to approximate f of 2.3. So f of 2.3 could be approximated by using the Taylor polynomial, the third degree Taylor polynomial, once I plug in a 2.3. So you would rewrite this and you would replace each of these x values with 2.3. I'll let you do that on your own. But we would get around 6.921. You might remember, by the way, the College Board doesn't quibble over equals versus approximation symbols. All right, so now we want to use the fourth derivative. And it says the fourth derivative of f satisfies this inequality that the fourth derivative of f evaluated at x, or in terms of x, is always going to be less than or equal to 9, or at least its magnitude, for all x values in the interval from 2 to 2.3. We are going to find a bound of error for my approximation of f of 2.3. Remember, this was an approximation because I didn't have the remainder, right? And if I wanted a truly accurate one, I would need to add on the rest of the remainder. So my job now is to try to figure out what the remainder is, because that's my error in the problem, and I'm going to use that error bound in order to do this. So in order to do this, I'm going to look at the remainder after the remainder that comes from my third degree approximation. Now I'm going to do the absolute value of that, because we could have some terms that have positive and negatives, and I always want error to be positive. So remember, this is another way to talk about my error, is to look at the remainder. Remainder will look at the next term. So since I did up to the third degree, I'm going to look at the fourth degree term for my Taylor polynomial. So I'm going to be taking the fourth derivative at some value of z. Evaluating at some value z. It doesn't actually, we're not going to know where z is. This is just representing the maximum of the fourth derivative. That's what that is. And then times x minus 2 to the fourth power over 4 factorial, because that's how we write the fourth degree term. And I always want the absolute value of this. So this is the actual remainder. This will be less than or equal to the error bound. Well, what was the maximum? I'll do an absolute value here still. What was the maximum that the fourth derivative could be? They said the fourth derivative would have to be less than or equal to 9. So the most it could be is 9. And then times x minus 2 to the fourth power over 4 factorial. And this would be on my interval from 2 to 2.3. So this is going to be the bound of the error. All right, now I want the bound specifically at 2.3. So this is my formula for the bound. So for the bound of the error, I want to take my remainder, my formula for the remainder for my third degree Taylor polynomial, and I want to evaluate it at 2.3. So I'm going to go to this and say this remainder should be less than or equal to, I'm carrying this over. This is the formula for the exact remainder, and then I'm approximating it because I'm only doing the max on a certain interval, okay? Not the max anywhere, but only on a limited interval, so I'm approximating it. Notice that 2.3 needs to be a part of this interval, as does the center. It's okay to be endpoints. So I'm going to say that this would need to be 9 times 2.3 minus 2 raised to the fourth power over 4 factorial. I would use my calculator, and I would get 0.00304-ish. So my error at most, and absolute value of my error must be less than or equal to 0.003. I want to use my answers from number 4 and 5 to find an interval. So a bound is different than an interval. When we talk about the error bound, we're talking about what is the max error. Error bound is asking for the max error, which is what we just did in number 5. But when we're talking about an interval, we want a high and low value. We want a range of values, a high and low value. Well, what I know is that f of 2.3, we had said would be, we thought it was around 6.921. Well, that value might be a little too big. That value might be a little too small. I don't know if this series is alternating. I actually don't have evidence from that. I don't think it's truly alternating exactly every other term. So I don't want to only add to the top or subtract from the bottom. What I want to do here is I want to take my approximation, which was 6.921, and I want to add on the error to the top, and I also want to remove that error from the bottom. Now you might notice I take this out to a couple extra decimal places. Actually, I think this was 6.92. I don't remember. I wish I'd written that out to more decimal places. I'm sorry that I didn't. I probably should have written that to 5 as well. But what this tells me is f of 2.3, once I go ahead and I do that adding and subtracting, is about 6, is going to be in between 6.918 and 6.924. This is an interval for the approximation. This is the error bound, the most the error could be. Please try to work on understanding the differences between them. So could f of 2.3 equal 6.922? Yes. Why? Because it is 6.922 is in the interval from number 6. So that is possible. Could it be 6.927? No, because the most the error could be was 0.003. And so 6.927, notice, is outside the interval. So 6.927 is not in the interval from number 6. And so I can't go that much. I already know the max that my error could be. All right, let's take a look at the last part of this. So we're going to be looking at the function f given by f of x is equal to the sine of 5x plus pi over 3. We want to let p of x be the third degree Taylor polynomial, but this is about x equals 0. Now this is problematic. You might be tempted to try to use a manipulation technique, but we can't do that. Here's why. This one is centered at 0. Where is this one centered at? Not 0. If I wanted to see where this one was centered at, I could set this equal to 0 to find out where this was centered at. And it's at negative pi over 15 for the center. But that's not at 0. Since they have different centers, I don't want to be tempted to use a manipulation technique. We should instead be using our old-fashioned rules of finding the derivatives and evaluating them at our new center, which is 0. So I'm going to ask you to pause the video and try that on your own and make sure you remember how to do that. I'm also going to pause my recording for a moment and then we'll compare in a minute. All right. So on this particular problem, just watch your chain rule, all right, for your multipliers of 5 as you go through and you do these. And then, yes, you do need to know how to evaluate all of your unit circle, and you do need to actually evaluate it before you decide you're done. But the third degree Taylor polynomial p of x centered at 0, I got as root 3 over 2 plus 5 halves x minus 25 root 3. Oh, I think I missed it too. Good thing I looked at this again. 25 root 3 over 2 times 2 factorial times x squared. Wow, I did awesome. Minus 125 x cubed over 2 times 3 factorial. Now I want to use the Lagrange error bound to show that f of 15 minus p, or f of 1/15 times p of 1/15 is less than 1 over 1200. So I'm going to encourage you to stop the video and to give this an attempt on your own. They're asking us to look at the remainder after our approximation through the third degree. So we need to be looking at the fourth term, and we're going to use the Lagrange error bound to try to figure out what the max fourth derivative would be, and then we'll compare from there. Now the goal on this one, I should have told you this, we're not going to use a calculator. You might be like, whoa, boy. There are times where you will be asked to not use a calculator. Now I might show a little more computation here, more simplifying on this than you would on the AP exam, because just a little bit more. I'm not quite in a testing environment, but I'm still not going to fully show every single computation because I'm going to do my best to not use a calculator either. We'll see how that goes. Well, I don't have, unlike the last couple examples, I don't really have a lot of information about the fourth derivative. On prior examples, one time they actually told me what the maximum of the fourth derivative in that notation. And another time they told me the maximum of the fourth derivative by giving me a graph and allowing me I could just choose the highest point. But this time they didn't do that. So I'm going to actually find the fourth derivative and see if that helps. So for my fourth derivative, if I look at my third derivative, my fourth derivative in terms of x could be found, let's see, I'll just take the derivative here. So this would be positive 625 sine, I already did my chain rule, already did my times 5, sine of 5 x plus pi over 3. Now let's think about what we know about sine. What is the most that sine could be? Well, if we think about the sine curve, the most that sine could ever be is 1, and the least it could ever be is -1. We're not going to be more than that. And then this has this multiplier 625. So what I know is that the max of my fourth derivative of x is going to be 625 times 1, or 625. This is the most that my fourth derivative could be. And I'm going to use this to talk about my Lagrange error bound. So I'm going to say that the most that my remainder could be, which is my error, my remainder calculated after the third degree, and I'll do in terms of x first, this would be found by doing the maximum of the fourth derivative evaluated at some point z times, now this time my center is 0, so this would just be x to the fourth, and then divided by the fourth factorial, and I do want this to be a positive right in here, so I'm going to use this absolute value notation. So the most that it could be is 625, because the most that sine could be is 1. Okay, the highest value sine could ever have. So this would be 625 x to the fourth over 4 factorial. Now what they want at most, and now these would be positive if x is positive, okay? Now, oh, actually, I guess since it's fourth power, do you really need the absolute value? I might just keep that in there, okay? Because it's kind of the form of the Lagrange error bound. So now what I'm going to do is I'm going to take a look at the remainder, evaluate the remainder from after the third degree Taylor polynomial, evaluate at 1/15, and the absolute value of that, because that's how we talk about error. So this could be found by saying, let's see, this would be less than or equal to the absolute value of 625 times 1/15 to the fourth power over 4 factorial. Now I want to somehow, without using a calculator, show that that is less than 1/20th. Now, if I were on the AP exam, I might just say that's less than 1/20th and move on because of time. But I do want to show you how could we figure that out. Well, 625 is really 5 to the fourth. And this is really 1 to the fourth from my numerator. And I have this 4 factorial. And then this 15 is also to the fourth, but that's to the denominator. But I could think of 15 to the fourth as 3 times 5 to the fourth, which could be thought of as 3 to the fourth times 5 to the 4th. And then this cancels out. And then that cancels out. So what would this all equal out? This would be 1 to the 4th, which is 1, over 4 factorial, which is 24, times 3 to the 4th, which is 81. Well, I know that 20 times 80 is 1600. Well, that is already less than 1 over, and I just did some approximation on here. And so I've used the Lagrange error bound to show that my error, which would be whatever 1 over 24 times 81 is indeed less than 1 over 1200. And that is the end of our notes for 4.8.